Okay, so um, I ended the um, re-upload of the last lecture that we did, um, which was spoiled by YouTube's bandwidth issues, with proof of the vector Thales theorem and the vector Pappus theorem. So if you haven't had a look at that, you can watch those later. We don't immediately need those necessarily, although uh, this is something that is going to be really nice for us going forward. And it's especially nice to actually see those in that form. So next, I want to discuss midpoints and centroids. And what's maybe a little ironic is, if I ask you to define what a midpoint is on a line segment, you would immediately go to references involving distance, right? So naturally, you would say that if I have a given line segment, so here's one, what's the midpoint of that line segment? Well, you would say it's half of the distance, so this is some distance between 2 points. The midpoint is just the point along this line that is at the halfway mark, right? It is half the distance between these 2 points. Now, what's funny is that we're actually going to define midpoints, and centroids are the more, maybe the higher D generalization, so that you're not just talking about midpoints of line segments, but you're talking about midpoints of some figure in the plane. Also, you can do this for space as well, as you've probably seen previously. So what's weird is that we're actually going to define these things before we define distance, okay? Which might seem a little strange, but to see how it is that we're going to do that and why we can actually do that without having the distance directly in front of us, note that if I have two vectors, so let's say this point, whatever it is represented by vector u, this one v, right? So each of these points correspond to some ordered pair, which I'm calling these vectors u and v. So note v is obtained from u by adding v minus u. And that might seem kind of silly, right? This is just the statement that v is u plus v minus u, right? Which algebraically, right, might look pretty silly, as this is a very obvious fact, but this is actually something important to notice here. Of course, this vector v minus u is our abbreviation for this line segment between these points represented by u and v, or that u and v represent. And so this, previously was our notion of the position of v relative to u, right? So this is the position of v relative to u. Right? That was how we defined this thing. We even treated this as an abbreviated form of writing this line segment. Okay. Thus, adding any multiple, say a times v minus u, to u, produces a point whose direction, this is direction in that sense we talked about in the last lecture, so whose direction relative to u is the same as that of v. Okay. Okay. Thus, another way of saying this is that the points of the form u plus some scalar multiple of v minus u, as I vary the scalars here, what are these points? These points are precisely those that are on the line through u and v. So the points u plus a times v minus u are precisely, that is not how precisely is spelled, are precisely the points on the line through u and v. Okay. Right. Thus, just intuitively, right, in particular, the midpoint of the segment between u and v is obtained by adding, well, exactly what you think, 1/2 times v minus u to u. All right. And so what is this midpoint? Oh, that's totally off. Pretend that I didn't totally... See, I covered up v with my hand here. This is totally off. Pretend this is the midpoint. So pretend this is the midpoint. The midpoint then is u plus 1/2 v minus u. But what is this? Right? This is actually, well, let's just rewrite it here. So midpoint of line segment between u and v is equal to u plus 1/2 v minus u. But using our vector space axioms, it's 1/2 v minus 1/2 u. So u minus 1/2 u. That's 1/2 u plus 1/2 v, or 1/2 u plus v. So our midpoint then intuitively is the average of the vectors, right? It's the vector average. So rewriting this, this is 1/2 u plus v here. Okay, which is exactly what you expected it to be. Okay. So the midpoint of our line segment can be thought of as the vector average of u and v, right? So midpoint of line segment between u and v is the vector average of u and v. Okay. Now, again, that might seem completely trivial, or completely something that you wouldn't even pay much attention to in terms of, maybe its importance to what we've already done. But note, this gives us a really easy proof of a fact that you did, I believe, in homework 2. This gives us a very short proof of a fact from, I believe this was homework number 2. Could have been number 1. I think it was number 2. So, very short proof of a fact from homework number 2. So the fact in question is that the diagonals of a parallelogram bisect one another. So diagonals of a parallelogram bisect one another. Okay, so let's, do I actually have my, well, let's draw a new one. It won't take that long. Okay, so let's draw the picture here. So say I have a diagonal, let's say that I have a parallelogram, and here's what two of its sides look like. Okay, so there's two sides. So we'll say here's vector u, here's vector v, and here's the 0 vector. So u plus v is the fourth vertex of this parallelogram. So here's u plus v. Okay. That's not the absolute best picture. Let's draw in these diagonals. Okay, so there's one, here's the other. Okay. Now, those look like they bisect one another, but why? Okay. Well, if I have parallelogram with vertices u, v, and 0, this other vertex is u plus v. The midpoint of the diagonal from 0 to u plus v is what? So that's this diagonal. So the longer diagonal in this case, the diagonal from 0 to u plus v, what's the midpoint of that? Well, to obtain that midpoint, what would I do? I would do the vector average of, so it'd be 1/2 times u plus v plus 0, right? So that's, this midpoint is 1/2 u plus v. But this is also the midpoint of the diagonal from u to v. So that's it, right? So those two line segments have the same midpoint, right? So they bisect one another. Okay. So really, really quick proof of this fact that you might recall previously what you had to do, right? Go back and look at your proof of this from homework 2 and see what it is you actually had to do to prove this, and it was slightly more annoying than this argument. Okay. All right. So what is the idea? So the concept of a vector average of two or more points is physically significant, right? So it's physically important since it is the barycenter or center of mass you've heard before. So it's the barycenter or center of mass of the system obtained by placing equal masses at the given points. By placing equal masses at the given points. Okay. So the geometric name for this for such a point is a centroid. Okay. All right, and so a vector average of 2 points is just a midpoint, but if it's, say, 3 points, 4 points, then ultimately the thing we get is similar in concept, but it's a slightly different thing. It's worth actually investigating on its own. So let's next we consider the case of triangle. Okay, so before I do that, I'd like to make a quick definition. So definition, I shouldn't say a median of a triangle is a line from a vertex of the triangle to the midpoints, or I should say to the midpoint of the side opposite the vertex. Okay. So the median of a triangle is a line from a vertex of the triangle to the midpoint of the side opposite the vertex. Okay. All right, and so I needed to define that so that I could state the following fact that I want to prove, which is theorem. This is on the concurrence of medians. So what this says is that the medians of a triangle pass through the same point, and that point is the centroid of the triangle. So the medians, right, there's 3. So the medians of a triangle pass through the same point. And this point is the centroid of the triangle. Okay. All right. So let's draw a picture. I'll try to have a good looking picture here. So okay, so let's say I have triangle. Say I have vertices U, V, and W. Okay. Then I have midpoints. Let's just kind of eyeball this. So there's midpoint. Of course, we can find midpoints using compass and straight edge constructions for any line segment if we want to, right? That's one of the first constructions we did, but we're being lazy. So here's another, and the other is here, roughly. What are these points? So this midpoint is 1/2 V plus W. This point is 1/2 U plus V. And this point is 1/2 U plus W. Okay, now if I constructed that perfectly fine, then what should happen here is that these medians, so median is from this vertex to the midpoint on the opposite side. Here's another median. And ideally, these would pass through the same point. I'm going to be slightly off here, but you get the idea. Okay. And this point is my centroid, okay, or the barycenter of this triangle. Okay. So here are three medians of the triangle. These three medians meet at the same point. That's the centroid. So that's what I'm trying to prove, okay? Now, given the triangle that I've drawn like this, when I draw in these midpoints, I know that those are the midpoints of those segments from previous comments. And so when I look at this, right, so for instance, just looking at this median from U to 1/2 V plus W, what does that look like? So note, what does it look like in terms of where this point lies as a proportion of this segment, right? So it looks like, right, and you might be very nervous already that I'm using this kind of language in a proof. Okay, but I'll explain how, like, all of this is actually rigorous. I'm just trying to show you, like, where you would come up with the intuition to say this. So looking at this picture, it looks like this centroid is 2/3 of the way out this segment. Okay, so it looks like the medians meet at the point 2/3 of the way from U to 1/2 V plus W. Okay, it just looks like that when I draw this picture. Okay, and so what this would mean, i.e., at the point U plus 2/3 times 1/2 V plus W minus U. Okay. Which is, so this is just, I'm just adding 2/3 of that line segment from U to 1/2 V plus W, right? So then going through this arithmetic, what do I get here? I have U plus 2/3 times 1/2, that's 1/3 V plus W, minus 2/3 U. But what is that? U minus 2/3 U plus 1/3 times V plus W is 1/3 U plus V plus W. Ah. Okay. So we're basically done. This is the centroid, right? By definition, the centroid is the vector average of three vectors. So U plus V plus W divided by 3, right? So 1/3 times U plus V plus W. So this point is the centroid. This looks like where these things meet, okay? But what does this mean? So similarly, this point is 2/3 of the way between, say, V and 1/2 U plus W. And 2/3 of the way between, I should say, W and 1/2 U plus V. Thus, the centroid is the common point of the three medians. Okay, so you may have some objections here because this seems like a really sketchy proof, right? How are any of the things that I'm claiming here following from this argument. The idea here is I use this word, I use this phrase, it looks like. This is my intuition from just looking at the diagram that I've drawn here, okay? So that is not part of the proof, really. This is just my guess. The point is, the second that I write this down algebraically, well, now this algebra says that this it looks like part was actually true. So when I write this statement out, this is saying, that centroid, right, or this supposed point where these three things meet, actually is the centroid, right? And it does lie. This first expression here says that it does in fact lie 2/3 of the way out of this segment here, out the segment from u to 1/2 v plus w, to the midpoint of the opposite side. Okay, and so what is the point, right? I could have, what that means is that I could have ignored this entirely and just started with this seemingly out of nowhere. And the second that I have this, no matter where it came from, once I have this and once I see I can do the same thing for the other segments, then I'm good, right? Then it doesn't matter, okay? But the idea, practically speaking, when you're trying to do these proofs and see what's going on, the idea is to actually predict the result using this intuition here, okay? And why is this nice? The idea is that when you compute this first thing and you say, the point 2/3 of the way from u to this opposite midpoint is 1/3 u plus v plus w, this is symmetric in u, v, and w. Okay, that's symmetric in u, v, and w. So when you get something like that, you have an expression that doesn't, sorry, I was off the page a little bit, that doesn't actually matter what order u, v, and w appear in, right? So once you have this expression, you can swap u, v, and w in any order you want to and trace the algebra backwards and get the same result for these other two things. There's no reason to compute these, right? i.e., no reason to compute the others. When I say the others, I mean these other two things I'm circling. You don't have to compute these at all because you can see that it's symmetric from the fact that you have said this expression is equal to an expression that is symmetric entirely in u, v, and w. Okay. And so they lead to the same results. There's no reason to actually do the other two calculations for that reason. Okay. So that's a neat fact. So it's kind of funny, as I said, that we discussed midpoints and centroids before actually talking about distance, right? That might seem a little strange. And as I previously mentioned, that in order to talk about distance, we need the inner product, okay? And so now we introduce that additional structure. So the way to think about this, or I should say the proper way to think about this, is you have a vector space. You can equip that vector space with an inner product. Now, we're going to do it in a specific way. The benefit of thinking in this way is that naturally this leads to a question of, what if I equip my vector space with a slightly different inner product? So an inner product that is not the same one I'm going to do here, or not the usual one, but follows algebraic rules similar enough to it that it still is geometrically, or in whatever setting I'm in, significant to me. Well, the idea is you get a different sort of space. And so thinking of like a hierarchy of structures you put onto an underlying space is one of the most powerful things that math did in the last 150 years. It is basically thinking of hierarchy of structures put on some underlying space where you can keep the underlying space the same and change the structure that you're putting on it, and this changes the thing that you are studying. It changes the quantities that maybe you're interested in into a slightly different setting. So the reason I'm going through this is, and I'll talk about this later, but for instance, if you want to switch from, say, Euclidean space to Minkowski space, which is not exactly Euclidean, and shows up, for instance, in Einstein's formulation of special relativity. If you wanted to switch to that space, essentially all you do is switch the product. Okay, you switch this inner product. Okay, and so I'll talk about that more. I'm kind of getting ahead of myself here. So what is the inner product, of course? So definition, we talk about this in R2, but this generalizes, of course, to, so it generalizes easily to R. And in fact, the primary setting in which you've seen the inner product previously is in R2 and R3. So I have vector u and v. These v's look like, and why do I have a bar here? This is no good. This is ugly. Okay, so vectors u and v, the inner product so we'll say inner product or scalar product or dot product. And we'll use those interchangeably. Of u and v is defined by, you already know what the dot product is. So u dot v is u1 v1 plus u2 v2. So I multiply the entries of these vectors component-wise and then sum. Okay. Okay, so that's the dot product of two. Vectors, it is a straightforward generalization to R3, right? You do the exact same thing where the vectors have three entries instead, so you get u1 v1 plus u2 v2 plus u3 v3, right? Okay, so of course, immediately you note the reason why scalar product is the thing that this is sometimes called is because you take two vectors and you product them in this way. You dot them together, and what you get is a scalar, right? So this is a scalar, not a vector. So it is not a proper product in the sense that it's not closed, right? You input two vectors, but the output is a scalar. So so it's not a thing that you would call a multiplication normally, right? It's some kind of different object. Okay, so we can check that it satisfies the following properties. So the following properties are: it is commutative. So it doesn't matter in what order you do this inner product. Okay, it is distributive with respect to vector addition. So the dot product of a sum is the sum of those things dotted. Okay. And lastly, behaves well with respect to scalar multiplication. In fact, you can pull scalars through this product entirely. So scalar multiplying in one slot in the product is actually the same as scalar multiplying in the other slot, or the same as doing the product and then scalar multiplying at the end. All right, so it behaves well with respect to the only other two vector operations I currently have before we introduce this, right? So the only other vector operations we have are vector sum and scalar multiplication. This behaves well with respect to both of those. Okay, but the real importance, so I always stress this even in Calc 3, but especially in linear algebra, the real importance of the inner product is its relationship to distance or length. So this is the thing that is important about the inner product. In fact, you could almost say that it is kind of the thing that determines, in some sense, the geometry. And so the imposition of this particular inner product on R2 is the thing that gives us the Euclidean geometry that we recognize, okay, that we've been doing this whole time. And so somehow Euclidean geometry is encoded in this inner product because this thing actually defines distance and length as we know it. That is the one that respects, say, the Pythagorean theorem. Okay. Okay. So and things like interior angle sums being pi. Okay. So what is the relationship between the inner product and distance or length? Okay. So the length that will be written as using absolute value bars of the vector, so we don't have these stupid norm double bars floating around everywhere. If you want to use the typical norm bars, that's fine too. It's not confusing because the context will be obvious when you're slapping these absolute value signs on a vector. We'll know what you're talking about. So the length, that is length of u, is the distance, right, of u, which has components u1, u2, from the zero vector, right? That's the completely obvious way that distance shows up, which is what? Which is from the zero vector, its components, of course, are 0, 0. Okay, and so this length is the square root of u sub 1 squared plus u sub 2 squared. Okay, so you already knew that. So then you say, why do I need the inner product before I can talk about this, right? I could have defined this the second that I realize, oh, wait, I have coordinates coming from all the stuff we built up in chapter 3. We have coordinates. Once you have coordinates, we have the distance formula, right, that we actually got from the Pythagorean theorem. So why do I need the dot product or the inner product to talk about this, right? Well, note what this actually is saying. Thus, if I look at the length of u squared, this is u sub 1 squared plus u sub 2 squared, right? It's just this quantity without the radical. Okay, but that's the vector u dotted with itself. Okay, and so it turns out, of course, you've seen this before, i.e., another way this is written sometimes is that, the length of u is the square root of the vector u dotted with itself. So you'll see this written in this way sometimes. And so this might seem like a backwards way of saying this, but actually the fact that this is the distance, or the thing that we think about as distance, is actually an artifact of this dot product. So again, this seems like a backwards way of thinking about it, but it's the dot product that gives us this distance. Okay, so the distance is a dot product. The dot product of a vector with itself is hiding in the formulation of the length of a vector, or the distance between two vectors. Okay. All right, and so this is the key thing that ties these together. And what this is said, like I said, interpreted properly, is that it's actually the inner product that gives us the distance. Okay. All right, so then also note that if I look at the length of the segment between u and v squared, what do I get? Well, according to this is v minus u dotted with itself, right? But I can use those properties of the dot product that I took away now, so let me bring them back. I can use these properties to simplify this. So I would have v dotted with itself, minus u, so this would be plus u dotted with itself, and then minus 2 times u dotted with v. So what is this? This is, I'll just write it out. So this is v dotted with itself plus u dotted with itself. After I simplify this, this would be minus 2 times u dotted with v. So I'm using the fact that u dotted with v is the same thing as v dotted with u. So when I subtract minus u dotted with v and minus v dotted with u, I get the same thing. So this is minus 2 u dotted with v. But I can replace these. This is the length of v squared plus the length of u squared minus 2 times u dotted with v. Okay, so this is another nice fact to note. You have almost certainly seen this expression before too, and actually it turns out this is the law of cosines from high school geometry, right? This is the law of cosines. So we'll see that. But this is actually the proof of the law of cosines. So if you remember using the law of cosines in high school geometry, the proof of this fact is exactly this expression. Okay, as we'll see. All right. Okay, this is one nice fact. Maybe I'll label that 1 here. Here's another nice fact. Note, of course, you already know this, but to recall why this is the case, note vectors u and v are perpendicular if and only if their inner product is 0. Okay. So this was actually, when you've seen the dot product for the first time, this was kind of the main motivating reason for defining the dot product, was being able to tell when two vectors were perpendicular. Okay, so why is this the case? So quick proof. Note that u has slope. If you think of the line from the origin to u, right? So if you think of the line in the direction of u from 0, this has slope. Rise over run is just u sub 2 over u sub 1. And v has slope v sub 2 over v sub 1. Right? And by homework, I think did I assign this? I don't think I've assigned this yet, so I will assign this from chapter 3. So by homework in 3.5 in the text, they are perpendicular if and only if the product of the slopes is 1. Maybe I can't remember if I signed this or not yet, but. And so that's it. Okay. So, two vectors are perpendicular if and only if their dot product is 0. That, of course, is a very, very important fact. As I said, your previous experience with the dot product, this is one of the most important ways in which you use the dot product, is to distinguish when two vectors are perpendicular. Okay, it turns out, though, that, of course, there's a lot more to these things determining angles or being related to angles between vectors that we'll discuss. So the last thing before I get into that, which will actually allow us to talk about angles or the cosine of an angle in a sensible way without having to do anything crazy like to talk about relative angles. So I have the following fact that I want to show, which is the concurrence of altitudes. Now, unlike the concurrence of medians, which you might consider to be somewhat kind of obvious, the concurrence of altitudes is not at all obvious. So in any triangle, I want to call this fact, but really this is a theorem that we're proving. Okay, so in any triangle, the perpendiculars. Oh, I am totally off the screen. So in any triangle, the perpendiculars from the vertices to the opposite sides these are the altitudes. So this is the definition of altitude of a triangle. Have a common point. So if you try to think about this for a second in your mind, as I said, this is unlike the concurrence of medians, which you might view as kind of sort of intuitive. This is less intuitive. And so what do I need to make this happen? So the main trick here is to take your 0 vector at the intersection of two of the altitudes, and to show that the other altitude has to also pass through 0. So I don't quite have time for that, so I will do this first thing on Monday so that I don't go over time. And so I think that's all I'll say today. This will be our first fact we use the inner product to nicely show before moving on and talking about the applications of the inner product to angles between vectors. And then we're basically getting to, we are not going to directly apply these things to three-dimensional Euclidean geometry, not right now anyway, but these sorts of arguments, the groundwork we lay, would allow us to do that if we wanted to, which would make it so much easier than doing this the way that Euclid did it. So the algebra, coming out of linear algebra and what it means geometrically, just makes all this sort of thing much easier. So anyway, that's the plan. So I will get close to finishing chapter 4 on Monday. Your first midterm will be not next week, but the week after. I think it will be that Wednesday. So I'll make another announcement about that. And also, I still haven't posted your homework 4, so I'll do that this afternoon, and it'll be due next week, like next Thursday or next Friday. So anyway, I will see you all on Monday.